The topic of today's lecture is Sylow's theorems, and we will begin with the definition of a p-group. Let p be a prime number. Definition. A group G is called a p-group if the order of G is equal to p to the power k for some k. Let us give a couple of examples. So if we take the dihedral group D4 or the group of quaternions Q8, so these groups have order 8. And thus these are two groups. As another example, consider the group of unipotent upper triangular matrices. So this is the set of matrices of the following type. So we have ones on the diagonal, 0 under the diagonal, and anything above the diagonal. And we consider these matrices in the group GLN ZP. So this means that we take these matrices over a finite field ZP. Then it's easy to count the sides of this group, and we see that the order of this group is equal to p to the power of n times n minus 1 over 2. So the order of this group is a power of p, and thus this is a p-group. Let the order of G be m p to the power n, where n is greater than 0, p is a prime number, and m is not divisible by p. A subgroup H in G of order p to the power n is called a Sylow p subgroup in G. So we know by Lagrange's theorem that the order of any subgroup is a divisor of the order of the group. So among p subgroups in G, the maximal possible order would be p to the power n, because this is the largest power of p that's a divisor of the order of the group. So the subgroups of G that are p groups and have this maximal possible order, so these are called Sylow p subgroups in G. Now let's consider the following example. So let's take as group G to be S4. So the order of S4 is equal to 24, which is 4 factorial. So this is 2 cubed times 3. There are two prime factors in the factorization of the order of this group. So it makes sense to talk about Sylow 2 subgroups and Sylow 3 subgroups. So Sylow 2 subgroup in G has order 8, and the Sylow 3 subgroup in G has order 3. Let us see if we can point out subgroups with these properties inside S4. So for the subgroup of order 8, we consider D4. So D4 is the dihedral group of symmetries of a square. So if we index the vertices of a square as 1, 2, 3, 4, then we see that the every symmetry of a square can be viewed as a permutation of 1, 2, 3, 4. And thus what we get is that D4 is a subgroup inside S4. And this subgroup has order 8. So this means that D4 is a Sylow 2 subgroup in S4. For Sylow 3 subgroups in G, so it's clear that if we take an element of order 3 in S4, then this element will generate a cyclic subgroup of order 3. So what we have is we can take cycle 1, 2, 3. So this subgroup generated by this cycle will have order 3, and thus it will be a Sylow 3 subgroup in S4. But we also can take a cycle 1, 2, 4, or a cycle 1, 3, 4, or a cycle 2, 3, 4. So what we see is that there are 4 Sylow 3 subgroups in S4. And for Sylow 2 subgroups in S4, so let us ask a question. How many subgroups isomorphic to D4 are in S4? So list all subgroups isomorphic to D4 in S4. Now let us formulate Sylow's theorems. We have first Sylow's theorem. So we state this in assumption that G has this order. G contains a Sylow P subgroup. So the first Sylow's theorem is the existence theorem. It claims that Sylow subgroups exist in any finite group for any prime divisor of the order of G. The second Sylow's theorem has 2 parts. So A, every P subgroup in G is contained in a Sylow P subgroup. And part B, all Sylow P subgroups are conjugate to each other. And the third Sylow's theorem tells us how many Sylow subgroups are there. It says that the number NP of Sylow P subgroups satisfies the following 2 relations. One is that NP is 1 mod P, and the second relation is that NP is a divisor of M, where M is this co-prime factor such that order of G is MP to the power N. All of these theorems are proved using the machinery of action of the group on the set. We begin with the following technical result that we will use later in our proof. Lemma. So let M be not divisible by prime P, then the binomial coefficient MP to the power N, choose P to the power N, is equal to M mod p. And hence, it's non-zero mod p. So for proof, let us write down what is the expression for this binomial coefficient. So mp to the power n, choose p to the power n, is equal to mp to the n times mp to the n minus 1 times dot 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 mp to the n minus p to the n plus 1 over p to the n factorial, which is the product p to the n times p to the n minus 1 dot 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 times 1. And this can be written as mp to the n over p to the power n times the product s goes from 1 to p to the n minus 1 mp to the n minus s over p to the n minus s. Consider a subring that we'll call zp with p in round brackets inside the field of rational numbers. So zp is the set of fractions a over b, where a and b are in z, but b not divisible by p. It's easy to see that the set of these fractions will form a subring inside the ring of rational numbers. And this subring is called localization of z at p. The nice thing about this subring is that here we can take remainders of fractions mod p. And thus we have a ring homomorphism from z localized at p to zp, the finite field of p elements. Obviously, we can do reduction of z mod p, but we cannot do reduction of q mod p. And the abstraction are fractions with p in denominator. So we cannot take 1 over p and reduce it mod p. And this localization ring is the largest subring inside q for which we can define the reduction mod p. Our claim is that for each s from 1 to p to the n minus 1, we have mp to the n minus s over p to the n minus s belongs to this localization. And if we call this reduction map pi, then pi of mp n to minus s over p to the n minus s is equal to 1. This means that each of these fractions will reduce to 1 in zp, and the first factor obviously is equal to m. And then this gives us the result that this binomial coefficient is equal to m mod p. To prove this, so we just write s as rp to the power k, where k is between 0 and it's strictly less than n, obviously, and r not divisible by p. So then mp to the n minus rp to the power k over p to the n minus rp to the power k is equal to, so we can cancel p to the power k, so we get mp to the n minus k, which is strictly positive, minus r over p to the n minus k minus r. And here we see that the numerator and denominator are no longer divisible by p, and they're equal mod p. And so this tells us that this fraction belongs to this localization of z, and the reduction mod p of this fraction gives us 1. And so from here we get that this is equal to m, and this proves the result that this binomial coefficient is equal to m mod p. And since m is not divisible by p, we get that this coefficient is non-zero mod p. Let's give the proof of the first Sylow's theorems. We consider the group action of G on the following set. Let M be the set of all subsets in G of size p to the power n. So here we just take subsets, not subgroups, just subsets. Then we know that the size of this set is the binomial coefficient, mp to the power n, choose p to the power n. So this is how many subsets with p to the power n elements we can choose. Consider the action of G on M by left shifts. So this means that rho of G acting on M is just G times M. We multiply every element of M by G on the left, and then we get another subset of the same size. Proposition. Let U be an element in M. So this means that U is a subset in G of size p to the n. Then stabilizer of U is a p subgroup in G. Let us prove the proposition. So let's denote the stabilizer by H. So what is this? So H is the set of elements H in G, such that when we shift U by element H, we get the same element U. Consider the following set. Let's multiply H by U. So we can write this product in two different ways. So we can write this as a union over H in H of H times U. But here, so each element H belongs to the stabilizer of U. So we see that this is U. But also we can write H times U as the union over U in U of H times U. And we see that this is a union of right cosets of H. Now, suppose we have S distinct cosets in this union. Then let's compare sizes of these sets. So the size of U is p to the power n by definition of M. But then we see that this set also can be written as the union of S right cosets of H. And each coset of H has size order of H. And from here we conclude that order of H is a divisor of p to the power n. And from here it follows that H, which is stabilizer of U, is a p subgroup, a p group. Now let us return to the proof of the first Sylow's theorems. So we consider orbits in M under the action of G. And we know that in this case, a set is a disjoint union of orbits. So since we know that the order of this set is not equal to 0 mod p by our lemma, so this implies that there exists an orbit O of U of length not divisible by p. So what we claim is that stabilizer of this set is a Sylow P subgroup in G. Let us write down our orbit stabilizer formula. So we know that the order of G is equal to the length of the orbit of an element times the order of the stabilizer of an element. Now, in this case, the order of the group is mp to the power n, and this equals to the length of the orbit times the order of the stabilizer. But we proved here in the proposition that the stabilizer is a p group, so its order is p to the power k. And here we have chosen an orbit such that its length is not divisible by p. And then comparing the left-hand side with the right-hand side, we see that k must be equal to n, and this means that stabilizer of this set U is a Sylow P subgroup in G. And this proves the existence of a Sylow subgroup in G. Let us give the proof of second Sylow theorem. So here we need to prove that every P subgroup is contained in some Sylow P subgroup, and that all Sylow P subgroups of G are conjugate to each other. Let K be a P subgroup in G. So order of K is P to the little k. And let H be a Sylow P subgroup in G. So order of H is P to the power n. And we proved that Sylow P subgroups exist. Again, we will be using the machinery of action. So we choose as our set M be the set of left cosets of H in G. And we know what is the number of left cosets. By Lagrange's theorem, so if the order of G is mp to the power n, and the order of a subgroup is p to the power n, then the number of cosets is equal to m. And this is not divisible by p. Now we consider the action not of G, but of K on the set M by left shifts. Our general theory says that M is a disjoint union of orbits. And by orbit stabilizer formula, we have that length of each orbit is a divisor of the order of the group, which is k, because we consider the action of k on this set, and which is a power of p. And thus, the length of each orbit is a power of p itself. However, the size of our set is not divisible by p. So, since the size of M is not divisible by p, and the size of each orbit is a power of p, so this tells us that there exists an orbit of some coset AH of length 1. This tells us that when K acts on this element, AH, so it is equal to AH, because for an orbit of length 1, the group must fix this element. And if we now multiply by A inverse on the right, we get that K times AH A inverse is equal to AH A inverse. And here we have a conjugate of a Sylow subgroup. And we know that the conjugate of a subgroup is a subgroup of the same size, because conjugation is an automorphism. And this implies that K must be inside the subgroup AH A inverse. So this tells us that K is contained in a Sylow subgroup. This proves the first claim of this theorem, that every P subgroup in G is contained in a Sylow P subgroup. The second claim of this theorem says that all Sylow P subgroups are conjugate. So if K is a Sylow P subgroup and K is inside AH A inverse. Now here we get that these two subgroups have the same size. They have size of p to the power n elements. So from here, of course, it follows that we have equality, that K is equal to AH A inverse. And this implies that K is a conjugate of H. And since H was an arbitrary Sylow subgroup in G, so this proves that every other Sylow P subgroup is conjugate to H. And this completes the proof of Theorem 2. Let us give the proof of the third Sylow theorem. So this theorem is about the number of Sylow subgroups in the group G. Let M be the set of all Sylow subgroups in G. So M, we can list them. So H1, H2, and we say that NP is the number of all Sylow subgroups. Now let us fix one of these subgroups. So let H be, say, H1, a Sylow P subgroup. We consider the action of H on M by conjugation. Let us look at the orbits in M under the action of H. So we know that the length of each orbit is a divisor of the order of the group. And so here we consider the action of H, and its order is p to the power n. So from here we conclude the length of each orbit is a power of p. Now let us study orbits of length 1. So suppose the length of the orbit of hi is equal to 1. So what does it mean? So this means that for all h in H, the conjugate of h times hi times h inverse is equal to hi. But then this tells us that h belongs to the normalizer of hi in G, where the normalizer is precisely the set of all elements with this property. But then hi also is a subgroup in its own normalizer. So clearly hi normalizes itself. Next, we apply Theorem 2 to the group Ng of hi, to the normalizer. So here we have that H and the hi are two Sylow subgroups in the normalizer, in Ng of hi. By Theorem 2, they are conjugate. So H and hi are conjugate in this normalizer. So this tells us that there exists an element h in the normalizer of hi, such that h is equal to h times hi times h inverse. But the element h is a normalizer, but the elements of the normalizer do not move hi. And we conclude that hi is equal to h. This tells us that there exists a single orbit of length 1. So what we proved is that if the orbit of hi is equal to 1, then hi is equal to h. And we conclude that in the action we have one orbit of length 1, and lengths of all other orbits are non-trivial powers of p. Since the set is a disjoint union of orbits, so we conclude that the number of elements in this set, which is the number of Sylow p subgroups in G, is equal to 1 plus a multiple of p. And this proves the first claim of the third Sylow's theorem, that the number of Sylow subgroups is 1 mod p. Now, the last claim of theorem 3 that we need to prove is, we need to prove that NP is a divisor of M, of this cofactor. To show this, we consider the action of G on the set M of its Sylow p subgroups. By theorem 2, all Sylow subgroups are conjugate. So we have one orbit O of H. And the size of this orbit is NP, the number of Sylow p subgroups. But then we know that the length of each orbit is a divisor of the order of a group. So this means that NP is a divisor of the order of the group, which is mp to the power n. But here we saw that NP is not divisible by p. And so here, if we have that NP is a divisor of mp to the n, and it's not divisible by p itself, so from here we conclude that NP is a divisor of M. And this completes the proof of the third Sylow's theorem. Now, let us expand our example of the group S4. So here the order of S4 is 3 times 2 cubed. So let us first take p equals 3. So what we see here is that every Sylow 3 subgroup in S4 has order 3. So this implies that it is cyclic and generated by an element of order 3. And the elements of order 3 and S4 are 3 cycles. So this tells us that the subgroups are generated by 1, 2, 3, and also containing a cycle 1, 3, 2, then 1, 2, 4, then we have 1, 3, 4, and finally 2, 3, 4. So the number of Sylow 3 subgroups is equal to 4, and we can see that this is equal to 1 mod 3. And it's also a divisor of 8, which is M in this case. We can also see that these subgroups are all conjugate to each other. So let us recall how conjugation acts in symmetric groups. So if we have a cycle I1, I2, Ik, and we conjugate it with permutation sigma, then the resulting will be a cycle sigma of I1, sigma of I2, sigma of Ik. So if we want to conjugate the cycle 1, 2, 3 into the cycle 1, 2, 4, then what we do is we take a permutation that switches 3 and 4, and if we conjugate 1, 2, 3 with the transposition 3, 4, then we obtain the cycle 1, 2, 4. And from here, it's easy to see that all these Sylow 3 subgroups are conjugate to each other. To see this equality, so we just look how the left-hand side acts on sigma of I1. So if we take sigma of I1 and apply sigma inverse, we will get I1. But then if we apply this cycle to I1, we will get I2. And finally, if we apply sigma, we get sigma of I2. And this shows that the left-hand side moves sigma of I1 to sigma of I2. And using the same argument, we see that sigma conjugates this cycle into this cycle. So in particular, conjugation preserves the length of a cycle in a symmetric group. Now let us take P equals 2. Sylow 2 subgroup in S4 must have order 8. And so we see that if we take D4, which is the group of symmetries of a square, then so D4 is a Sylow 2 subgroup in S4. Now let us look at subgroups of order 4 in S4. One class of such subgroups are cyclic subgroups generated by 4 cycles. But that's not all. So we also have Klein 4 group, so which is denoted V4, which is the following subgroup in S4: identity 1, 2, 3, 4, 1, 3, 2, 4, and 1, 4, 2, 3. From here, we see that subgroups of order 4 are not conjugate to each other in S4, because conjugation preserves the cyclic structure, and the Klein 4 group does not have 4 cycles. So this means that a cyclic subgroup generated by a 4 cycle is not isomorphic to V4. Or another explanation to this is that V4 is not a cyclic subgroup. So here we see that P subgroups need not to be conjugate, but Sylow P subgroups by Theorem 2 are conjugate to each other. Now we also see that if we take a 4 cycle 1, 2, 4, 3, then it's not contained in D4 that corresponds to this square. So this gives us an example of a 2 subgroup which is not in this Sylow P subgroup. And by Theorem 2, every 2 subgroup must belong to some Sylow P subgroup. So this tells us that there is more than one Sylow 2 subgroup. And then we conclude that the number of Sylow 2 subgroups is equal to 3, because it is a divisor of 3 and it's different from 1. And we also see that this is in agreement to the third Sylow's theorem. So 3 is equal to 1 mod 2.